This question is about period 3 of the periodic table. So you count down your periodic table, hydrogen and helium being period 1, lithium to neon being period 2, and sodium to argon being period 3. Deduce which of Na plus and Mg2 plus is the smaller ion. This is quite a common question, trying to catch you out a tiny little bit, because you would look at sodium and magnesium and you would look and see that magnesium has a higher atomic number, and you might think, well, more stuff, that's going to make magnesium bigger. This question is secretly about the electron configuration. Remember that the protons and neutrons are confined within that very small nucleus at the centre of the atom, and the electrons in the shells are really going to determine the size of our atom, or in this case, ion. So if we think about sodium and magnesium, sodium is number 11 in the periodic table, so a sodium 1 plus ion has 11 protons and 10 electrons in shells. So if we think about that overall, we've got 1 electron in the first shell and 8 electrons in the second shell in s&p orbitals. And then if we look at magnesium, which is a 2 plus ion, it's got 12 protons, but because it's a 2 plus ion, it's also got 10 electrons. So these two ions both are identical in electron configuration. They are isoelectronic. So they have the same number of shells with electrons in them, but magnesium has got more protons in the nucleus, so it's got more pull from that nucleus onto those two shells of electrons. So it pulls those two shells in just that tiny bit tighter, and so we'd say that the smaller ion is magnesium 2 plus, and we would say that they have the same electron arrangement, or the same number of electrons. So both ions have the same number of electrons. They're isoelectronic. But Mg2 plus has more protons. What does that mean? Mg2 plus has a stronger nuclear attraction to the electrons. And so for the 2 marks, you don't actually need that final sentence. They're looking really for Mg2 plus because it has more protons but the same number of electrons. So you need all of this sentence for your first, for your mark, and this correct selection for your other mark. Now we're being asked to write an equation for first ionisation energy. So it's a secret way of testing whether you know the definition. So the definition being the energy required to remove 1 electron from each atom in 1 mole of gaseous atoms. So from an electron, or a mole of electrons from a mole of atoms, or 1 electron from each atom in a mole of gaseous atoms. So it's all in there, sodium gaseous atoms, and we're trying to remove a mole of electrons. What would that leave us with? It would leave us with sodium positive ions in the gaseous state. So that's our answer to that one. Okay, first ionisation energy of some period 3 elements are shown below. Complete figure 1 by adding in magnesium and sulfur. So bearing in mind that this is atomic number 11 is sodium, so magnesium is going on this line of number 12, and then after number 12 we go to aluminium, silicon, phosphorus, sulfur, chlorine, argon across period 3. So we're being asked to put in magnesium and sulfur. We can see that the crosses are missing on the graph here. And we need to know the pattern. So this is really asking you, do you understand that as you go across this period, that your electron configuration goes from 3s1 all the way across to 3s2, 3p6. So sodium is 3s1, and then argon at the end is 3s2, 3p6. And what is happening to electron configuration? How is that being reflected in first ionisation energy? So we know that magnesium, if we think about the electron configuration of magnesium, it would end up being 3s2, and sodium was 3s1. So it's the same subshell. There's no change there, but there are more protons in the nucleus. So we need our cross to be higher than sodium's. We would like it also to be higher than aluminium's, and the reason for that is that it doesn't continue up from sodium to magnesium to aluminium, because remember that aluminium's electron configuration goes 3s2 3p1, and as a result we're getting a new subshell. So our cross must be above this 600 line because aluminium's just below it. We don't want to be above silicon really, so we kind of want to be aiming in the middle of between where aluminium and silicon are. So we get this up to magnesium and then down to aluminium and then back up to silicon. Then what happens at sulfur? Well, phosphorus, if we think about that, is 3s2 3p3 and sulfur is 3s2 3p4. So what's happening at sulfur is we're starting to have to pair up in p orbitals. So we've gone along, if you think we're going at sodium, 3s1, and then magnesium, we're putting a second electron in there, 3s2, and then we've gone to aluminium with an electron in the p orbital, silicon, 2 in separate orbitals, phosphorus, 3, and now at sulfur we have to pair up, and that creates a tiny repulsion, and so our cross needs to be below that of phosphorus, so below the cross for phosphorus, but above the cross for silicon. So we need to be in between here and here, phosphorus and silicon. So we're going somewhere in that gap. Just rub those little marks out. I'm going to put my cross somewhere here in between those two. So we get this pattern of up, dip for the new subshell, carrying on up, dip for pairing in a p orbital, carrying on up. This is a standard shaped curve. So explain why you've done what you've done. So we've scored 2 marks already for our 2 crosses. Explain why you've done what you've done for sulfur. And so you need to say, at sulfur, the electron has to pair up. Now we need to be specific here. In a 3p orbital. Now, you can't just say p orbital because sulfur's got 2 p orbitals as well. In a 3p orbital. Then this causes a repulsion. So less energy is needed to remove the electron. What we're seeing there is that this repulsion means less energy is needed to overcome that attraction from the nucleus.